Let's now convince ourselves that the protocol for 1 out of 2 oblivious transfer is actually secure against cheating Bob. At least if his quantum storage is small enough. Let's first have a quick look at the protocol. I've removed all the actions by Bob since they can now be arbitrary. If we want to analyze the security of quantum protocols, it helps to think like an adversary. So go and imagine that you are in fact Bob, and your goal would be to learn both strings S0 and S1. What would you do? Let's for the moment think what would happen if Bob had a perfect quantum memory. He can store n qubits. Let's imagine that we are cheating Bob and try to attack the protocol. If we want both S0 and S1, we have to come up with a strategy for Bob to guess both of these strings, the entire string X. So how can we do that? You may want to think about this for a second before continuing. If we are cheating Bob, and we have an arbitrary quantum memory, note that one thing that we might do is to simply store all the qubits that Alice is going to send to us. We don't measure anything, we just store them, and we keep them all the way through the waiting time. We wait until Alice announces her basis string theta, and then we measure every qubit in the right basis, and we learn the entire string X. Because remember, if we measure in the same basis that was used by Alice, we get the same outcome. So if Bob has a perfect quantum memory, it is certainly not possible for his min entropy to be larger than 0, or equivalently, his probability of guessing the string to be less than 1. Something has to happen in this waiting time. With the storage assumption, we take advantage of precisely this step. We will now do the security analysis in 2 steps. First, we will purify the protocol, and you've already learned what this means. Here, we are going to apply it to protocols in the noisy storage model. Let's purify. As before, instead of preparing BB84 states, so instead of choosing a bit X and the basis theta and preparing the bit in the chosen basis, Alice is going to prepare EPR pairs. She keeps the first part, the A part, and she sends the second qubit B over to Bob. Let's say they do this n times, one after the other. For each of these EPR pairs, both Alice and Bob will now measure in a basis. Alice chooses a random basis string, theta A, Bob chooses a random basis string, theta tilde B. And they're going to measure, which gives them some outcomes. So Alice measures the qubit in basis theta j to obtain outcome xj. I'm not writing here what Bob does, because remember that Bob is cheating. So he might do anything. In particular, he might try to measure some of these qubits, giving him some classical information k. He might apply a crazy error correcting code that is arbitrarily complicated to stuff something into his storage device, which I will call Q. Note that this purified protocol is completely equivalent to the BB84 protocol. So why is purification actually convenient here? Let's have a look at just one round of the protocol. So n is 1. In the end, remember that we wanted to establish something about the min entropy. But the min entropy of the strings corresponding to the standard and the Hadamard basis. Let's start by thinking about the min entropy that Bob has about the entire string X. Let's say we want this to be large, of course. So the min entropy of X given Bob. This min entropy, of course, depends on whatever Bob has, which is as follows. He has whatever is left from his quantum storage device, which we called Q. He has the classical information K. Maybe he measured some of these qubits. And he has the basis information theta. So the first step that we're going to make is that I want to eliminate the quantum memory. So let me make some space here. So here we have two classical systems, K and theta, and whatever is left from his quantum storage device, Q. Let's try and get rid of that. And we can do this in a very straightforward way, namely by using our usual trick. We can observe that the min entropy about X given K, theta, and Q is never smaller than the min entropy given just K and theta minus the log of the dimension of Q. So this here is just the number of qubits that Bob can store. They're much more sophisticated analyses than this one, and you can find pointers to them in the lecture notes. But here, let's take this simple perspective of eliminating Q. Remember that the min entropy depends on the probability of guessing the string X. So let's think about the probability of guessing X in just one instance of the protocol. In one instance, Alice prepares an EPR pair, namely this one. She keeps A and she sends B to Bob. Alice picks a basis, theta, and gets a measurement outcome, X. Remember that after we remove the quantum storage Q, we're only interested in Bob's ability to guess using classical information. So we're basically in a scenario in where Bob cannot store anything. So we can think that Bob will just measure his qubit B and get some classical information K. After the waiting time, Bob now only has K and Alice sends him theta. At this point, Bob has the classical information K and the basis information theta. And from these two together alone, he should make a guess for X. Why does this bias anything? Purifying the protocol, so far so good, but why is that interesting? We will now take a small step that will bring us back to familiar territory. Namely, we will actually give Bob a little bit more power. Remember that here Alice had created the initial state, the EPR pair, and Bob could just measure the qubit B. Note that conditioned on K, he may of course have prepared some state in Alice's lab. This gives him more power because we imagine he can now actually send the qubit to Alice. For example, in the EPR pair case, if he measured in a standard basis, it might be 0, 1, but note that Bob cannot say whether it is 0 or it must be 1. So allowing him to actually send a state to Alice, he can decide it will be 0 or it will be 1, gives him slightly more power. We can have some classical information K, of course, And depending on K, you could decide on different states to send to Alice. So to summarize, we can imagine we are in the following situation. Bob gets to prepare a state, rho A. Alice chooses a basis, theta. She later tells Bob which basis she's chosen, and Bob's goal is to guess Alice's measurement outcome, X. This should sound very familiar to you, because we have discussed such a situation at length in the beginning of our course. Namely, we are exactly back to our uncertainty game. In the uncertainty game, we have analyzed exactly what is the adversary's probability of guessing X if Alice measured in the standard or in the Hadamard basis. So let me just remind you what this guessing probability was given by. So this guessing probability, P guess, maximized of all possible states that Bob could have prepared, given theta A, and if we want also K, is roughly 0.85. Or if we remember the exact value, a half plus a half, 1 over square root 2. In terms of the min entropy, this means that for one round, the min entropy is roughly the log of that. So for one round, for one bit, so to say, we have a min entropy of X now being 1 bit, K theta A being minus the log of the guessing probability being roughly 0.22. There's a simple argument starting with the end of the string that you can find in the lecture notes, which shows that also if for the entire string, the probability that Bob guesses Alice's entire string X, even if you could prepare a huge state rho across all n qubits, is given by just n times the min entropy for 1 bit. So this means that if we now go back to the case where we do this n times, the min entropy that Bob has about the entire string X, so I'll put an n here to indicate that we're looking at the entire string, theta A, so theta A of course being for all the n bits, K is roughly 0.22 times the length of the string. So we thus see that we can get min entropy from quantum uncertainty. So the min entropy of the entire string is given by this uncertainty game, if Bob had no quantum memory. So what's next? Remember that we can, of course, incorporate the storage by just subtracting it. But of course here we're not interested in the min entropy of the entire string. We're interested in the min entropy of the two pieces. We want that one of these two parts has large min entropy, because we'll hash these two parts down to two different keys, K0 and K1, and Bob should not be allowed to know one of them. Thankfully, there's a powerful technique known as min entropy splitting that was first introduced by Jörg Muhlschläger. Unfortunately, it only works if the system that we condition on is classical. But this is the case here because we removed Q. We condition on K and theta. The min entropy splitting theorem, which you can find in the lecture notes, says that there exists one string, XD. So my big X consists of two parts, namely all the pieces where I measured in the standard basis and all the bits where I measured in the Hadamard basis. And min entropy splitting tells me that there exists some d, namely one of them, such that Bob's min entropy about xd, namely precisely this part, so either this one or that one, is roughly the original min entropy divided by half. So I'm saying roughly because we subtract here a minus 1. So if we remember how much min entropy we actually had, remember that our min entropy was roughly 0.22 times n. So I divide that by 2 minus 1. So we have roughly 0.11 times n minus 1 bits of min entropy. So let's use this. So remember that in the security analysis, we want to show that there's some input that Bob cannot learn. And this is equivalent to showing that there exists one of these two keys, KD, that he cannot learn. And we can do that by showing that the min entropy of XD is large. Let's introduce the quantum storage back into the mix. First, we can remove the quantum storage by lower bounding the min entropy that Bob has about XD by this, minus the number of qubits that he can store. So this is the number of qubits Bob can store. Now we can apply the min entropy splitting theorem. So this tells us that we can relate the min entropy of this part to the total min entropy divided by 2. So if I plug this in, it means that my total min entropy is roughly 0.11 times n minus 1 minus the number of qubits that Bob can store. So how do we use this in the protocol? Remember randomness extraction. We know that an extractor can extract roughly L being equal to the min entropy, in this case xd d k theta a q minus order log 1 over epsilon many bits. If we want the output to be epsilon close to uniform for the adversary. So the output, namely my key, in this case KD, given all of the information that the adversary has, let me just all of that call E, is then epsilon close to uniform on KD, tensor rho E. So this means that we can now extract these L bits, which are almost perfectly uniform, and in our protocol, L is the length of the string S. So SD has length L. So we thus gain a key of length L, and we can use it to one-time pad encrypt SD. So if we assume that Bob never has more than q qubits of quantum storage, and we want security with some parameter epsilon, then we can now solve for n in order to find out how many qubits we need to send. So this is fixed by my desired accuracy. This I can rebound by this term, where q is also fixed. So the only free parameter is n. So I have to determine how many qubits n do I need to send. We will see that security can in principle always be achieved. We just need to make n large enough.